Creatine is one of the most popular and extensively researched dietary supplements in the world. Yet, despite decades of scientific research, many misconceptions still surround its use. Some people believe that creatine is unsafe and may damage the kidneys, while others think it causes hair loss, muscle cramps, or excessive water retention. Many people also associate creatine only with bodybuilding and gym training, leading to questions such as: can non athletes take creatine? Is it beneficial for general health? How much creatine should be taken each day? Is a loading phase necessary? And for how long can creatine be safely consumed? In this video, we will answer all of these questions by exploring what creatine is, how it is synthesized and stored in the body. We will then discuss its effects on exercise performance, muscle growth, and overall health, review evidence-based dosing strategies, examine the different types of creatine available, and finally address the most common myths and misconceptions surrounding creatine supplementation. By the end of this video, you will have a clear, science-based understanding of creatine and whether it deserves a place in your health and fitness routine. Creatine is a naturally occurring and nitrogen-containing compound comprised from amino acids that belong to the family of guanidine phosphagens. To understand where creatine comes from, it is important to know that the body can produce it on its own through a series of biochemical reactions. Creatine synthesis begins primarily in the kidneys, where two amino acids, arginine and glycine, are brought together by the enzyme arginine-glycine amidinotransferase. This reaction produces an intermediate compound called guanidinoacetate. Once formed in the kidneys, guanidinoacetate is released into the bloodstream and transported to the liver. In the liver, guanidinoacetate undergoes a methylation reaction catalyzed by the enzyme guanidinoacetate N-methyltransferase. During this process, a methyl group donated by S-adenosyl methionine is added to guanidinoacetate, converting it into creatine. After creatine is synthesized in the liver, it enters the bloodstream and is distributed throughout the body. Most of the creatine is then taken up by skeletal muscles, where approximately 95% of the body's creatine is stored. Smaller amounts are transported to other tissues with high energy demands, such as the brain, heart, and testes. Within the muscles, roughly 2/3 of creatine exists in the form of phosphocreatine, which serves as a rapid energy reserve, while the rest remains as free creatine. Together, these forms make up the total creatine pool in the body. In addition to the creatine produced naturally by the body, dietary intake also plays a major role in maintaining healthy creatine levels. In fact, endogenous synthesis provides only about half of the body's daily creatine requirement. Therefore, the remaining amount must be obtained from food sources, particularly red meat and fish, or through dietary supplements. For a typical 70 kg individual who regularly consumes meat and fish, total muscle creatine stores are approximately 120 millimoles per kilogram of dry muscle mass. However, dietary habits can significantly influence these levels. For example, vegetarians often have muscle creatine and phosphocreatine stores that are 20 to 30% lower than those of non-vegetarians because they consume little or no dietary creatine. As part of its normal metabolic cycle, a small portion of the body's creatine pool is continuously and irreversibly broken down. Approximately 1 to 2% of the creatine stored in muscle is converted each day into creatinine, a waste product that is released into the bloodstream and eventually excreted in the urine by the kidneys. This rate of breakdown tends to be higher in individuals with greater muscle mass and in those who engage in high levels of physical activity. Consequently, daily creatine requirements vary depending on factors such as diet, muscle size, and activity level. Once creatine reaches the muscle through the bloodstream, it enters muscle cells via specialized proteins known as creatine transporters. After entering the cell, creatine is present within the cytosol, the fluid portion of the cell where many metabolic reactions occur. From there, a portion of the creatine diffuses into the mitochondria, which are often referred to as the powerhouses of the cell because they are the primary sites of ATP production. Within the mitochondria, the enzyme mitochondrial creatine kinase is present. As in the mitochondria, ATP generated through oxidative phosphorylation interacts with this enzyme. This enzyme transfers a high-energy phosphate group from ATP to creatine, converting creatine into phosphocreatine, while ATP itself is converted into ADP. The newly formed phosphocreatine then diffuses out of the mitochondria and returns to the cytosol. In this way, this phosphocreatine serves as a carrier of high-energy phosphate groups, transporting stored energy from the mitochondria to other regions of the cell where energy may be required. This continuous movement of creatine and phosphocreatine between the mitochondria and the cytosol is known as the creatine phosphate shuttle. The importance of this shuttle becomes particularly evident during exercise. To understand this process, it is important to remember that ATP or adenosine triphosphate is the immediate energy currency of the cell. During muscle contraction, ATP is continuously broken down into adenosine diphosphate and inorganic phosphate, releasing the energy required for muscular work. However, the amount of ATP stored within muscle cells is very limited and can support maximal effort for only a few seconds. Therefore, as exercise continues and ATP levels begin to decline, ADP starts to accumulate within the cell. At this point, phosphocreatine, which was previously synthesized in the mitochondria, acts as an immediate reserve of high-energy phosphate groups. Through the action of the enzyme creatine kinase, phosphocreatine donates its phosphate group to ADP. As a result, ADP is rapidly converted back into ATP, restoring the cell's energy supply. Simultaneously, phosphocreatine loses its phosphate group and becomes free creatine. The newly formed ATP can then be used immediately to support continued muscle contraction, while the free creatine can return to the mitochondria, where it can once again accept a phosphate group and be converted into phosphocreatine. Consequently, this cycle allows ATP to be regenerated rapidly during periods of high energy demand. For this reason, the phosphocreatine system serves as the body's first and fastest energy buffering system, particularly during short duration, high intensity activities such as sprinting, jumping, and resistance training. Furthermore, its role extends beyond exercise. For example, in conditions where oxygen availability is reduced, such as ischemia or hypoxia, or in situations where energy demand exceeds the body's ability to produce ATP, such as mental fatigue or certain disease states, the creatine phosphocreatine system helps buffer energy levels and support normal cellular function. Therefore, the overall function of creatine is to ensure that cells have a rapid and continuous supply of energy whenever ATP demand suddenly increases. Now that we have understood how creatine works within the cell, it is easier to appreciate its practical benefits. As by increasing phosphocreatine stores in muscle, creatine helps regenerate ATP more rapidly during periods of high energy demand. As a result, individuals are often able to perform more repetitions, sustain higher training intensities, and recover more effectively between bouts of exercise. As a result of these physiological effects, creatine supplementation has consistently been shown to increase intramuscular creatine and phosphocreatine stores, enhance exercise capacity, and improve training adaptations over time. In practical terms, individuals who supplement with creatine are often able to perform more repetitions, lift heavier loads, maintain higher training intensities, and recover more effectively during training sessions. These benefits have been observed across a wide range of activities, including resistance training, running, swimming, soccer, and other high intensity sports. Furthermore, research has demonstrated positive effects in both men and women and across various age groups. Overall, the scientific evidence supporting creatine supplementation is exceptionally strong. In fact, major organizations such as the International Society of Sports Nutrition consider creatine to be one of the most effective nutritional supplements for enhancing high intensity exercise performance and promoting gains in lean body mass. Therefore, creatine is widely recognized as a safe and effective ergogenic aid for athletes, recreational exercisers, and individuals seeking to improve their health and fitness. Beyond its well established effects on exercise performance, growing evidence suggests that creatine may also provide several health benefits throughout the lifespan. For example, studies have suggested that creatine may help improve blood lipid profiles by lowering cholesterol and triglyceride levels, support liver health by reducing fat accumulation in the liver, and contribute to cardiovascular health by lowering homocysteine levels, a risk factor for heart disease. Furthermore, creatine has been shown to possess antioxidant properties, which may help protect cells from oxidative stress and damage. Research has also indicated that creatine may improve blood glucose regulation, support healthy aging by preserving muscle mass and strength, and potentially help reduce age-related bone loss. In addition, emerging evidence suggests that it may enhance cognitive function, particularly in older adults, improve functional capacity in individuals with conditions such as osteoarthritis and fibromyalgia, and in some cases, enhance the effectiveness of certain antidepressant treatments. There is also preliminary evidence suggesting that creatine may play a supportive role in slowing the progression of some forms of cancer, although further research is needed in this area. Taken together, these findings suggest that creatine is more than just a sports supplement. By supporting cellular energy production throughout the body, creatine may contribute to overall health, physical function, and well-being as individuals age. Therefore, many researchers have proposed that a daily intake of approximately 3 grams of creatine may be beneficial for supporting long-term health and healthy aging. Now the dosing. The optimal dose of creatine depends largely on the intended goal. For athletes and individuals performing high-intensity activities, the primary objective is to rapidly increase muscle creatine stores and maximize phosphocreatine availability. To achieve this, the most commonly recommended strategy is a loading phase followed by a maintenance phase. During the loading phase, creatine monohydrate is consumed at a dose of approximately 0.3 grams per kilogram of body weight per day for 5 to 7 days. For a 70 kilogram individual, this corresponds to roughly 20 to 25 grams per day, typically divided into 4 5-gram servings throughout the day. This approach can increase muscle creatine stores by approximately 20 to 40% and achieve near maximal muscle saturation within about 1 week. Following the loading phase, a maintenance dose of 3 to 5 grams per day is recommended to sustain these elevated creatine stores and compensate for the small amount of creatine that is naturally lost each day through conversion to creatinine. An alternative strategy is to consume 3 to 5 grams per day from the outset without a loading phase. Although this approach increases muscle creatine stores more gradually, research has shown that similar levels of muscle saturation can be achieved after approximately 3 to 4 weeks of continuous supplementation. This approach is often preferred by individuals who wish to avoid the transient increase in body mass that may occur during the loading phase or who prefer a simpler dosing regimen. In contrast, for individuals who are not engaged in intense training but are interested in supporting general health, healthy aging, cognitive function, muscle preservation, or overall creatine status, a loading phase is generally not necessary. In these cases, a daily intake of 3 to 5 grams of creatine monohydrate is typically recommended. As individuals age, they often experience a gradual decline in muscle mass, strength, and physical function, a condition known as sarcopenia. In addition, older adults may consume less dietary creatine due to reduced intake of meat and fish. Consequently, many studies investigating healthy aging, muscle preservation, bone health, and cognitive function have utilized creatine supplementation in this population. The most commonly recommended dose is 3 to 5 grams of creatine monohydrate per day, often combined with resistance exercise to maximize benefits. Although some studies have explored higher doses, a daily intake of 3 to 5 grams remains the most practical and evidence-based recommendation. Now, the timing of creatine supplementation. Current evidence suggests that the total daily dose is more important than the precise timing of ingestion. Nevertheless, consuming creatine close to an exercise session, particularly when combined with carbohydrates and/or protein, may modestly enhance muscle creatine uptake due to increased insulin-mediated transport. Therefore, many practitioners recommend taking creatine either shortly before or shortly after training, although consistent daily intake remains the most important factor. Now, let's briefly discuss the different types of creatine available on the market. Among all the available forms, creatine monohydrate remains the most extensively studied and is widely considered the gold standard. Decades of research have consistently shown that it effectively increases muscle creatine stores, enhances strength and exercise performance, and has an excellent safety profile. In addition to creatine monohydrate, several other forms are available, including creatine HCl, buffered creatine, creatine ethyl ester, creatine citrate, and creatine malate. While some of these products may dissolve more easily in water or claim better absorption, current scientific evidence has not shown them to be more effective than creatine monohydrate. Therefore, based on effectiveness, safety, and cost, creatine monohydrate remains the preferred choice for most individuals. Now, after the dosing and types of creatine supplementation, let us address some of the most common misconceptions surrounding creatine. First one is, does creatine cause water retention? This belief originated from some of the earliest creatine studies, which reported increases in body water during the first few days of supplementation, particularly when high loading doses of approximately 20 grams per day were used. As a result, many people came to believe that creatine causes excessive water retention and bloating. To understand this issue, it is important to remember that creatine is an osmotically active substance. That means, when creatine enters muscle cells, water is naturally drawn into the muscle cell to help maintain fluid balance. Therefore, some increase in water content within the muscle is expected, especially during the initial stages of supplementation. However, this should not be confused with undesirable fluid retention under the skin or generalized bloating. Importantly, numerous long-term studies have shown that creatine supplementation does not cause abnormal increases in total body water, extracellular water, or fluid retention. Instead, any increase in water content primarily occurs within the muscle cell itself, known as intracellular water. In fact, this increase in intracellular water is considered a positive adaptation because it creates a more favorable environment for muscle growth and protein synthesis. Therefore, the current scientific evidence does not support the notion that creatine causes excessive or harmful long-term water retention. Rather, the water associated with creatine supplementation is primarily stored within muscle tissue, where it may contribute to improved muscle function, recovery, and training adaptations. The second common misconception is that creatine supplementation causes kidney damage or impairs kidney function. In fact, this is one of the most persistent myths surrounding creatine. Despite more than 2 decades of scientific research demonstrating that creatine is safe for kidney health when consumed at recommended doses by healthy individuals. Much of this misconception stems from confusion between creatine and creatinine. As discussed earlier, a small portion of the body's creatine and phosphocreatine is naturally broken down into creatinine, a waste product that is filtered by the kidneys and excreted in the urine. Because blood creatinine levels are commonly used as a marker of kidney function, some people mistakenly assume that an increase in creatinine following creatine supplementation indicates kidney damage. However, this is not necessarily the case. Creatine supplementation can slightly increase blood or urinary creatinine levels simply because more creatine is available for normal metabolism, not because the kidneys are functioning poorly. Furthermore, considering that millions of athletes, exercisers, and recreational users have consumed creatine supplements over the past several decades, there is no evidence of an increased incidence of kidney disease attributable to creatine supplementation. Therefore, based on the current scientific evidence, creatine supplementation at recommended dosages appears to be safe for kidney health in healthy individuals. Nevertheless, as with any dietary supplement, individuals with pre-existing kidney disease or other medical conditions should consult a healthcare professional before beginning supplementation. The third common misconception is that creatine supplementation causes hair loss or baldness. This concern largely originated from a single study involving college-aged rugby players, which reported an increase in levels of dihydrotestosterone following creatine supplementation. Because elevated DHT levels have been associated with hair loss in genetically susceptible individuals, many people began to speculate that creatine might contribute to baldness. DHT is a hormone produced from testosterone through the action of an enzyme called 5-alpha reductase. In individuals who are genetically predisposed to male pattern baldness, DHT can contribute to the gradual shrinking of hair follicles over time. Although the study reported a rise in DHT levels after creatine supplementation, the increase remained within the normal range for healthy individuals and no actual hair loss was observed in the participants taking creatine. Since then, numerous studies have examined the effects of creatine supplementation on testosterone and related hormones. The overwhelming majority of these studies have found no meaningful increase in total testosterone, free testosterone, or DHT levels following creatine supplementation. Therefore, there is no convincing evidence that creatine supplementation causes hair loss or baldness. The fourth common misconception is that creatine supplementation causes dehydration and muscle cramping. This belief became popular because creatine increases the amount of water stored within muscle cells, leading some people to speculate that it might draw water away from other parts of the body and increase the risk of dehydration, especially during exercise in hot environments. As a result, concerns emerged that creatine users might be more susceptible to muscle cramps, heat-related illness, or dehydration. At first glance, this theory may seem reasonable because creatine is an osmotically active substance and does increase intracellular water content, particularly during the initial loading phase. In fact, many individuals experience a small increase in body weight during the first week of supplementation, largely due to increased water stored within muscle tissue. However, the important question is whether this actually leads to dehydration or muscle cramping in real-world settings. When researchers began investigating this issue, the scientific evidence did not support these concerns. Although some surveys reported that athletes believed creatine caused cramping or dehydration, these reports were based on self perception and often involved individuals consuming doses higher than recommended or using other supplements simultaneously. In contrast, controlled research studies have consistently shown that creatine supplementation does not increase the risk of dehydration, muscle cramps, or heat related illness. In fact, some studies have reported the opposite effect. For example, athletes supplementing with creatine during training and competition experienced fewer episodes of muscle cramping, dehydration, heat related illness, and muscle injuries compared with non users. Therefore, creatine supplementation does not appear to cause dehydration or muscle cramping when consumed at recommended dosages. The last common misconception is that creatine supplementation increases body fat or causes fat gain. This belief likely arises because some individuals notice an increase in body weight after starting creatine and assume that this additional weight must be fat. However, scientific research does not support this conclusion. As discussed earlier, creatine supplementation can increase body weight, particularly during the initial stages of supplementation. But this increase is primarily due to greater water retention within muscle cells, and over time, increases in lean muscle mass rather than an increase in body fat. In fact, numerous studies conducted in athletes, recreational exercisers, older adults, and clinical populations have consistently shown that creatine supplementation does not increase fat mass.